Where's Fernando? How are we going to get that vector that is sticking out of this plane orthogonal to it?
First, you got to get the magnitude, so you got to square them all and add them.
Magnitude of what?
Or, no, I'm sorry, no, you got to.
That's right. If you're not sure.
You can do like 1 time. It has to equal 0. No. Yeah, 0, right? If you do the dot product, then they're orthogonal.
I think you're overthinking it.
You find 2 vectors between those
Yeah.
points.
Yeah, if you're not sure, it's okay.
Oh, okay.
I mean, we're here to learn, right? So this is where you say, okay, yeah, I thought it might be that, but no, it's not that, right? What are you thinking?
You find the 2 vectors between the points.
Okay, so we look at this, we say, okay, this creates a plane, like there's a triangle, right? But that's really a plane, and you're saying create 2 vectors from this. Yes. We want to create 2 vectors on that plane that go from, any point to any other 2 points. So it doesn't matter how you do this. So maybe like this and that right there. So let's label these points. Let's let this one be the 1, 2, 14. Let's let this one be the -2, -5, -1. Let's let this one be the 12, -3, and then 1. So we've got those 3 points. We're creating 2 vectors on that plane. Why are we creating 2 vectors on that plane? What are we going to do with them?
You want to find that normal line,
That
vector.
we're trying to find that normal vector, the one that's sticking out perpendicular to these, right? So after you find these vectors, you're just going to cross them up, right? Okay. So let's get these vectors. How about the vector, this vector right here? What is that? In its component form, Rose, you're up. So I'm looking for the vector from here to here.
So
11,
-1,
-1, wait, hold on.
like,
11, I agree with 11.
oh,
Then
sorry,
this, -5, okay. And then
and then
-13. Okay, so that's one of your vectors. And then how about, let's see, Milton? Is Milton around today?
That's me.
That's you. Okay, so Milton, you get the next one. This vector from here to here.
So, -2 minus 1 would be -3.
-3,
-7.
-7,
And -15.
and -15. Right? We all on board? Now we get to cross them. And when we cross them, that's going to create this vector, right? It will be a normal vector. It will be a vector that is orthogonal to both of those vectors, right? So we have just taken this. We've created 2 vectors. And now we're going to cross them, and it will create a vector that points out this way. Now, remember from last class, I said that when you cross, the order matters, right? So if I cross one way, I'm going to get this vector, right? If I cross the other way, I'm going to get the vector that's on this side of the page like that. Doesn't matter. Doesn't matter. N can be any vector that is orthogonal. And both of these are orthogonal. So it doesn't matter which one. Doesn't matter which order you cross these, is what I'm saying. So my normal vector is going to be the cross product of -3, -7, -15 crossed with 11, -5, -13, right? That's what it's going to be. Do we remember how to cross product? Yeah, I rewrite them on top of one another and then cover things up and do little determinants and remember that the middle sign changes and all that fun stuff. Okay, 11, -5, -13. All right, here we go. Go ahead and, play on your own. Maybe you can help me. I don't have a calculator. I might need one. Let's see, 70, is that 91 minus 75? $70, $80, $91 minus 75, I think, right? 75, 80. Is it 16 on that first one?
Yep.
Okay, 16. And then the middle one I cover, 39 plus, oh shit, I'm getting my calculator out. Is it 115 in the middle? And you changed the sign already? Yes? Oh, okay. So negative 116? Are we going to just trust that answer, everyone? Yes? We have, okay. Let's have at least 2 people verify it. Not that I don't trust you, it's just I don't trust you. I don't trust me, I want someone to verify for me, so this is the arithmetic stuff. By the way, a lot of your calculators can do cross products. And even if you have an older model like TI-83 or TI-84, you can write a program to do it. Just Google it, like cross product program TI. Yes? You had negative 200 in the middle?
Yeah.
Uh-oh, okay. So let me see here. 3 times 13, and then minus plus.
Should be negative 3 times negative 13 minus negative 13 times.
So what we should have is negative 3 times negative 13 minus 11 times negative 15. But then whatever that answer is, we're going to change to the sign. So it's this times this minus this times this. I'm getting 204. I'm getting 204 from this. And then I have to change it to negative.
Oh yeah, I was for mine.
And 92 for the last one.
You got 92 for the last one? Okay. You got something different?
I got 92.
You got 90? Okay, so we have at least 2 92s. We'll go with that. Okay. There it is. That is the cross product. Now those are big numbers, aren't they? And I could use this as my n. But because the numbers are big, I'm going to see if I can make it a little bit smaller. I'm trying to shrink this vector. I can stretch it, right? I can shrink it or stretch it. That won't change the direction. So if I can find numbers that go into all these, like I know 2 goes in, right? 4 goes in also. Goes in 4. How many times 4 go into that?
51.
51, so minus 51, and then 4 goes into there?
23.
23. That vector would also qualify as a normal vector, and it's smaller numbers. Just divided everything by 4. Just happened to work out that way, all right? Like if this were like 91 or something, we would just be stuck with this big ugly vector. So my normal vector is the vector, the normal vector that I am going to use, all right? The normal vector that I'm going to use is this. Okay? And this, remember, is, well, that's your A, your B, and your C, and this is your x naught, y naught, z naught, and now you go straight to the equation, which I erased. I said I was going to leave it up there, then I erased it. So the equation is A, x minus x naught, plus B, y minus y naught, plus C, z minus z naught equals 0. That is your standard equation of a plane. But now A, B, and C are these numbers, and then x naught, y naught, z naught are those numbers. So it's going to be 4 times x minus 1 minus 51 times y minus 2, and then plus 23 times z minus 14 equals 0. Yes?
I have a question. For our x naught, y naught, z naught, could we pick any one of those?
Any of those points you could have picked. You like the smaller numbers here? Or,
No, I was just asking.
yeah, no, any of those points would work. Any of those points would work.
Okay.
So here's what I'd like for you to do right now. I'd like for y'all to go ahead and distribute the 4 through, the 51 through, and then you're going to have a bunch of constants when you do that, right? Like you're going to have like 4x, then you have this, and then y'all do that. In the meantime, what I'm going to do over here is I'm going to do what you suggested. I'm going to do a different point. Okay, and let's see if we get the same answer. Now, we're still using the same normal vector. So I'm going to do 4. Let me know if anyone gets that. I boxed it over there. Hopefully I did my math right. You got that? Okay, that's reassuring. Thank you. Okay, so this is what I got when I distributed, and then if you collect all your like terms together, we should all get this right here. So what that means is that some amazing way, as long as the point you're picking lives on the plane, as long as we're all using the same n, we're all going to get the same answer at the end. That means the equation is unique. This is a unique equation. More than that, here's something really important. What if I started a problem out right now and I said, hey everyone, here's the equation of a plane, right? What is the normal vector of this plane? What's the normal vector of that plane? Do you see how easy it is to find it? It's just the coefficients, isn't it? 4, negative 51, 23 is the normal vector, always. So if you ever have an equation of a plane written out like this, that number, and that one are your normal vector, the coefficients. Very easy to grab the normal vector from the equation of a plane. And that is super important. Questions on that? Well, what if we're trying to determine the angle between two planes? So let's say somebody gives us a plane, and then gives us another plane, and we're trying to find the angle between them. So that would be like, I have two planes here, right? This one's like this one's like that, whatever, they're sitting there. So imagine, they extend, so they hit somewhere, right? They hit somewhere like this. And I'm trying to find the angle between. They don't have to be 90 degrees, okay? They could be like that, right? So I'm trying to find that angle between them. If I'm trying to find that angle between them, how in the heck are we going to do that? So here are two planes, right? I'm trying to get that angle so we can see it right in there. We're trying to find that angle between them, right? So one thing we could do is we could just figure out the normals of each plane. So the green plane, boy, this is really a weird skewed view. It's really hard to tell that green vector is orthogonal. I think I can convince you this way. Okay, so you see this green vector? It is the normal vector of that plane. And then the orange vector is orthogonal to the orange one, if I can do that. There we go. See that? So their normal vectors are just sitting out there, right? And remember, the normal vector sticking out of this plane can be slid around anywhere, right? Because it's just a direction. So now let's move those normals close to one another. So I'm going to slide those normals so that they're right next to one another. I'm going to take the other ones out. And I want you to notice something. Losing it. Do you notice something? It's the angle between the vectors, the normal vector, is the same as the angle between the planes. Because, if this one has a normal vector is 90 degrees, right? Then whatever other plane is out here, its normal vector, they're both off by 90 degrees to the direction of the plane. So that means that the angle between these is equivalent to the angle between the planes. So that angle is the same as that angle. Those are the same. So how do you find the angle between two planes? You just find the angle between the two normal vectors. And how do you find the angle between two vectors? That formula from the other class. with the dot product. Okay, so let's do it. Oh yeah, by the way, two planes are parallel if and only if they're normal vectors or are scalar multiples. So when you have two parallel planes like this, they're parallel, then when you look at their normals, they have to be pointing in the same direction, don't they? Or, well, not same direction. They could be opposite direction, but they have to be parallel, right? Two planes are perpendicular if and only if their normal vectors are perpendicular. In other words, if you take the two normal vectors and dot them and get 0, then the planes are orthogonal, aren't they? Find the angle between these two planes. I have two planes, P1 and P2. All right, Ricky, where's Ricky? Ricky, what's the normal vector of plane 1? 1, 1, 1. Okay, good. And then I'm doing this more just to get through the attendance, okay? Paul? Okay, Paul, what's the normal vector of plane 2?
2, -4, and 7.
Okay. We all agree? Just make sure that when you do this, all your x's, y's, and z's are all on one side of the equation. So like in other words, if this 4y was over here, you'd have to bring it over here to be able to pull off the coefficient. Now, let's say somebody's like a complete rebel, and they take the 2x to the other side, the 4y to the other side, and the 7z to the other side. They take it all over there. They're going to get a different answer, aren't they? But it's going to be a scalar multiple, right? So it's okay. It'll just be pointed in the other direction, that's all. Okay, so here are two normals. Okay, could I, if I wanted to, use -3, -3, -3? Right here. Yes, I could, right? Just trying to point out some things. I mean, the normal vector, they just have to be scalar multiples in order to qualify. All right, so this is normal of plane 1, this is normal of plane 2, and we're trying to find the angle. So let's see, we had the formula. It was theta was arc cosine of u dot v over magnitude of u times magnitude of v. That was our formula for finding the angle between two vectors u and v. So for us, we want the angle between these two. So even though I'm not going to write it down, we're going to treat this vector kind of like the u, and we'll treat this vector kind of like the v is in the formula. All right? So let's try and get this. Theta is, Domingo, you been getting enough rest? Tired? You okay? Life okay with everything? Good. What's that? Yeah, yeah. Okay, Domingo, what's the dot product of those two?
The dot product is 2 minus 4 plus 7.
Okay, so 2 minus 4 negative 5? Is that 5? Arc cosine of 5 over, okay, we need some magnitudes here, right? All right, what about the magnitude of this one? So you just like square all these, right? And then add them together, and then take the square root. So root 3, right? Root 3, right? That, add them up. Root 3. So root 3, and then root, let's see, square each of these and add them up. So 4 plus 16, 20, and then 49, so 69. So root 69. And then now it's calculator time. And have you done it? You look, okay, you looked like you had. You got to make sure you know what mode you're in, because let's take the answer in, what do you want, degree? Yeah, let's do degrees.
Just shy of 70 degrees? Yeah.
70-ish?
69.66.
Okay, so it's approximately 69.6 degrees. That's the angle between those. Yes?
For our tests and our homework, how many times do you want us to round, or how many places do you want us to round to?
Yeah, that's not a big deal for me. Like I wouldn't round that up to 100. 69.6, you could say 70 degrees. I'm more concerned about seeing the work. I always look at, we're not building a bridge right now. We're not trying to put a man on the moon. We're just trying to calculate. So if you want to go, whatever your judgment is on that. That seem fair?
Yeah.
I'm not real particular about it, honestly. Yes, okay. Lots of major ideas here. Finding the line of intersection of two planes. So let's say that two planes hit one another, right? Let's say that two planes intersect. Wherever they hit each other, they form a line, don't they? Wherever they hit one another, that's a line. Can we actually find the equation of that line if somebody just gives us the equations of the planes? Should be able to, but it seems like it might be tedious. No, does it not seem tedious? I think it's actually pretty nice what happens here. Okay, we have two planes. Do you see the blue line on those two planes where they hit each other? Here's the way I want you to think about this. We want to be able to find the equation of the line of intersection of the planes, right? What do you need to define the equation of a line?
2 points.
Okay, 2 points, college algebra. Cal 3, we need we need exactly what?
The directional vector.
A direction vector, which is v, and we also need some initial vector or some initial point, right? So, watch how I'm going to do this. Let's go after the direction vector. Let's go after v. Can we find the v of that line? Well, here's how we do it. Each of those planes has a normal vector, right? Okay, let's slide those normal vectors down to where the line is. Okay, you'll see the normal vectors there? Let's cross those. If we cross those normal vectors, that vector is living on the same direction as the line, isn't it? And that gives us v. So it's very simple. If somebody gives you two planes and you want to find the direction vector of the line of intersection, you simply cross the normal vectors of the planes. Now that just gives us the direction vector. What do we still need? Some initial point. Well, that's any point on the line, right? And any point on this line would be any point that satisfies both equations of the planes at the same time. So we'll get to that, but this is actually not going to be as difficult as it might seem. So here we go. We've got these two planes, right? We are trying to find the vector equation of the line of intersection of these planes. So what we're trying to find, we want r of t, which is equal to r naught plus tv. All right, let's go after v first, because v is actually easier to get than r naught. So how can I get v? And let's see if any of that, what I just said, sank into Audrey's head. Let's see if anything I just said sank into Audrey's head.
Will that be 1, 1?
Okay, so we're going to try and get the direction vector of the line, which you're saying is going to be taking the normal vector of this plane, which is 1, 1, 1, and doing what with it? It's all right. So if we want the direction vector of the line of intersection of two planes, we need to cross the two normal vectors of the planes. So you told me the normal vector of the first plane was 1, 1, 1. And I'm going to cross that with what? 2, negative 4, 7. Right? Have we crossed those? We have not crossed those, have we? So this will be the first time we're crossing these? Okay, so this will be, well, let me do it. It's 1, 1. Let me do it up below this. So 1, 1, 1. Cross that with 2, negative 4, 7. Let's see, 7 plus 4. 11. 7 minus 2 is 5. Change it. Negative 5 and negative 4. Take away 2. Negative 6. Anyone else get that? For the cross of those?
Oh, 7 minus negative 4. Okay,
Yeah, 7 minus negative 4.
I got that.
Okay, we're good? So what we've done, again, imagine you've got two planes, right? And they had two normal vectors. And what we've done is we've taken them and crossed them, which gave us a vector coming out that's actually running parallel to the line of intersection. Now we just need a point on that line. So now we need this. So any point that we can find that would be both here and here. So that means you have to now find an x, y, z that satisfies this and this together. So how many unknowns do we have? How many equations? 2, which means, well, we won't have a unique solution. We actually have an infinite number of solutions, which makes sense because there are an infinite number of points on that line, right? So this is now it's up to you. You need to try and give me, find an x, y, z which satisfy plane 1 and plane 2 equations. That makes sense? You give me an x, y, z that will make the first and second ones true, or the first plane equation and second equation true at the same time. So one easy way to do this is to just come in here and just fix one of the variables. We did this once already. Do you remember me doing that? Like I said, hey, look, I'm going to try and figure out where these two, I don't remember when we did it now that I think about it, but we did do it. So I'm going to who cares? I'm going to let z be 0. If z is 0, then what do these two equations become? X plus y equals 5, and the other equation becomes 2x minus 4y equals 10, right? So I can just move that 10 over. If my z is 0, that's what I've got. Now I've got two equations, two unknowns. And I can solve this using elimination or substitution. I still like elimination. How would you do elimination here? Like if it were up to me, I'd multiply the top equation by negative 2. That's the way I would do it. And then I would just make this negative 2x minus 2y equals negative 10. The bottom equation doesn't change. And, what am I going to get here? I'm going to get 0. I'm going to get negative 6y equals 0. Well, that's okay, because that means y is 0, right? So if y is 0, what's x? 5. And just go back over here, let y be 0, x then is 5. So that implies that x is 5. So have we found a point? 5, 0, 0. So that is a point. The point 5, 0, 0 lives on that, lives on the intersection of those two planes. Could I have chosen z as 1? Sure. Okay. Yeah, go for it. I'm not sure how your math is going to work out, but 0 is always a good one. You could have also done x is 0, and then you would have had an equation with y and z in it over here. It's up to you. This is why I don't want to grade 8 take-home exams. If everyone's doing something slightly different, it gets really hard to grade, because everyone's answer is going to start looking a little different, or their work's going to look different. All right, I think we're ready for the equation. R of t equals, okay, what's R naught? It's this written as a vector, right? It's the vector 5, 0, 0 plus t times the normal vector, which we got from crossing, right? And then you could put that all together, right? Into one vector equation. So 5 plus 11t, negative 5t and negative 6t. And here t is an element of the real numbers. So if you sketch this, it'll draw the line that intersects, that forms the intersection of those two planes. 10 minutes, 10 minutes. Distances. May I erase? Yes, okay. Last topic of this section. There's two main things we're going to do right now. Hopefully, I don't know how much in 9 minutes, but we are going to, this is the first of the two things. We won't talk about the other one. We're interested in finding the shortest distance between a point and a plane. Somebody gives me a point in three-dimensional space. Somebody gives me a plane in three-dimensional space. Measure the shortest distance between that point and that plane. And I showed this to you all way at the beginning of this section, I think, on dot products. I said if I'm trying to find the shortest distance between some arbitrary point and some plane, the first thing I do is I pick a point on the plane, any point, pick any point, and then I draw a vector that goes from that point to that, the point on the plane up to the point. This is the point that was given to us. This is the point I picked, right? How would I pick a point off a plane?
Arbitrarily?
Just arbitrarily. Just give me an x, y, z that make the equation of the plane true. Now, the vector I draw from here is not orthogonal, right? It's just arbitrary. Then I calculate, or I get the normal of the plane. Now, the normal vector is easy because if someone gives us the plane equation, we can see it easily, right? Just the coefficients. So that's an easy vector to get. Not cross them. Then we imagine shifting that blue vector over, which doesn't require any change in the vector because they can slide around, right? They're all equivalent. But visually, just move it. And then we project it. So remember there was projections, the calculations we had, there was formulas for projection of u onto v or component of u onto v. We will project it, the blue onto the red, and then we'll measure its length. So we are actually looking for the component of the blue onto the red. Shit. These planes are parallel. How could you convince me of that very quickly? Their normal vectors are scalar multiples of one another, aren't they?
Yeah.
The normal vector of this one is 1, 1, 1. The normal vector of this one is 2, 2, 2. 1, 1, 1, 2, 2, 2. Those are scalar multiples. So these planes are parallel. We want to find the shortest distance between these planes. What do you think the most common answer I get is for this?
2.
For the distance between them?
Yeah, sure. 2. That's 15. Minus 4.
I usually get 5 is the most common answer. So think about it. If you take plane 2 and divide everything by 2, what would you get?
You get 10 on the other side.
You get x plus y plus z equals 10, right? And so then the only difference between those two equations is 5 and 10, right? So you think, oh, okay, that means there's a difference of 5 between them. It's completely wrong. Okay, it's completely wrong. These planes are at an angle, right? So it's not that simple. So how do you think we can do this? I just gave you a way of finding the distance between a what in a plane?
Point.
A point in a plane. Well, just pick a point, right? So look, we have one plane here, right? We have another plane here. They're kind of skewed out. Instead of looking at this as distance between plane and plane, why don't we just pick a point on this plane, throw it out the door, and then find the distance between that point and that plane. Yeah? It would be the same distance, shortest distance. Okay, so give me a point off this one right here. Give me a point. Any point that would live on that plane. So point on plane 1 would be 500. I like that one. I like how many zeros you used. Everyone agree with that? That is a point that lives on that plane. So now visually, here's what I have. A point. That is the point 500. Now we have a plane sitting here. This is the plane 2x plus 2y plus 2z equals 20, right? That's that plane. That's this. So now what I need to do is pick some point on this plane. So somebody give me a point on that plane. 10, 0, 0. Everyone agree? I think it works, right? 10, 0, 0, 10, 20, right? So that point lives on the other plane, yeah? Agreed? Now what I'm going to do is I'm going to draw a vector that goes from here to here. What's that vector that goes from there to there?
-5.
So this vector is the vector from here to here, -5, 0, 0. Awesome vectors that we have here. Great. Now we need another vector. What's the other vector that's very important in this problem? The normal vector of the plane. Okay, so what's the normal vector of this plane? And that would run, it would go up like this, right? And it's orthogonal to the plane. So what's that vector? 2, 2, 2. Could I use 1, 1, 1? Yes, I could use 1, 1, 1, but I'm going to go with 2, 2, 2 so that everyone knows where it came from. It's the normal vector of this plane. Now, what? We want to project which one onto which one? This doesn't have to go through that point, but it kind of helps that it looks like it does. We're going to, imagine taking this one, right? Moving it over, and then projecting it onto the red one. Does that look blue to you? Did you say blue?
I said blue, is it not blue?
It's purple. I mean, does it look purple to y'all or blue?
More like a violet, maybe?
Yeah, violet, whatever. Yeah, I know on camera that it doesn't come out very good. So since we don't want to go with colors here, why don't we just call this one U, okay? And why don't we call this one over here V? So we want to project U onto V, don't we? But do we really want that? That answer is what? When you do a projection of a vector onto another vector, your answer is a? Nope.
It's another vector.
It's another vector. We don't want that. We actually want the length of that vector, right? And that's the other one. That's component of U onto V. That's that one. This would give us a vector. I don't care about the vector. I want to know how long that vector is, because the length of the vector, when you project this onto that, I don't have another color. Well, I have green. But when you project this vector onto that one, you get that distance. And that distance is what I'm interested in. All right, so does somebody have this formula handy on how we find that?
U dot V over the magnitude of V.
U dot V over the magnitude of V?
Yes. And I looked at my notes, I in no way.
Oh, I forgot the magnitude, sorry. You looked at your notes and what?
I in no way remember that.
Yeah, it's okay. I mean, I think for the most part, everything you're going to be doing is at home, so you'll have access to the formulas. And then when it comes to the test, the midterm, we'll talk about what you can bring. And I'm going to let you all bring formulas to the test. All right, so we just need to compute this, right? Man, that dot product is super clean, isn't it? What's the dot product?
-10.
-10? 0, 0? Okay, so just -10. And then over the magnitude of V. Magnitude of v is that squared plus that squared plus that squared, root 12. Now, I know you might be freaking out because it's negative, and you're thinking this is length. But if you look back in the notes, all that meant is that our one vector is like this, and we're trying to project onto this vector right here. So when we project it, it's on the back end of it. And so it's back here, so it's on the other side. So that's why it's negative, yes?
So our normal is pointing on the other.
Yeah, in other words, when I drew it, the normals pointed a different direction. Or the normal's in one direction and this vector's on the other side of the plane. It's okay though, because all we care about is this as a number. Let's go ahead and get that as a decimal. What is that as a decimal? 10 over root 12. Oh, I'm out of time. Jonathan, Christopher, and Aaron. Yes? All here? Jonathan, Christopher, and Aaron. All right.
It's 2.89.
2.81? 89?
Yeah.
Okay.
I'm sure it's negative.
Yeah, it's negative here, but in terms of the distance, we will just say that it's, absolute value. So the distance between those planes is about 2.9-ish units. Minimum distance between those two parallel planes. All right, everyone. I don't think... yeah, we have one more topic there. Just one more thing. Shortest distance between a point and a line. So you have a point, you have a line now going through space. Shortest distance between the two. We'll get to that next time.